And I would say at this point of this class, being able to read ahead is actually quite important because everything is building upon the previous topic. Like I wouldn't say rapidly, but I would say it is. We don't have time to spare to dwell on some topics that we have already talked about. So, kind of important to read ahead of me, because otherwise, the final exam, well, okay, exam two is on Thursday. It's not going to be too brutal, but the final exam will be brutal for people who are falling behind in terms of understanding the concepts. All right, so what we'll do is we're going to go to the caller-callee agreement today, and it describes basically the contract between the caller and the callee on multiple things. We'll focus on two things today. One is the return value of a function, and then the second one is our parameters. So we are not going to talk about local variables just yet, but we will talk about how a value is returned from a function, and also how do we pass parameters from the caller to the callee, and how does a callee access the parameters that are passed to it. So that's going to be the focus of today's class and also today's lab. Okay, so that means you might need to write down some notes. Everything that is on the projector is recorded, but you need this content to do the lab, so you might want to write it down just so that you have this material available when you are doing the lab. This document, once again, is linked from inside Canvas. So if you go down to Canvas, from your perspective, it is a lot cleaner. So after the lab from last Thursday is caller callee agreement and also parameters and local variables. So that's going to be what we will be focusing on in today's lecture. So there we go. Okay, we'll go over stack operation. This is nothing new. Okay, the stack operation specification is something that we talked about before when we talked about just function calling and returning. In other words, I'm only describing, what it is like to push something on the stack, which is described by this quote unquote RPN. No, RPN, this is a RTL. So we pre-decrement the stack pointer, which I choose the register D to be, and then whatever it points to is going to store the value that I am pushing on the stack. So in TTP, this X can only be the four registers, A, B, C, or D itself. In other words, you can, if you want to, push register D itself on the stack. The stack pointer can be pushed on the stack. I have not found any use for that to happen. Okay, but if you need it to happen, it can happen. So, so this is nothing new, just presented a little bit differently from the previous module. And then the instruction to do that, it looks like this. Okay, your pre-decrement register D right here, and then store the reference, your register D, and then you specify X, which basically is one of the four registers, and that goes here. So this part should be not new at all, okay, compared to what we have already talked about in the previous class. So the next one is how do we, once we store something, once we push something on the stack, how do we pop or retrieve that information from the stack? So this is how we do it, this is how we pop something from the stack. It is exactly the reverse of the operation. We dereference the post increment of the stack pointer and then store whatever that is to X, which can be one of the four registers again. Okay, so once again, this is a slightly different presentation of what we talked about when we talked about calling and returning, but it's essentially the same thing. And then the assembly instructions to do just that is also described here, which is starting with the LD because we are retrieving first before we increment the stack pointer to quote unquote deallocate whatever the stack pointer was pointing to, so that the stack pointer is now pointing to the item that was pushed before the item that is now retrieved. All right, so do we have any questions about this material at this point? I believe this was talked about last Tuesday, because last Thursday we talked about the practice exam. So this is from last Tuesday. But the lab of last Thursday is about this. So more or less, just a review at this point. So now I assume we can move on, or are there any questions? Okay, there are no questions. All right. So the way because of the stack convention, items that are pushed early occupy memory locations that are higher in addresses. For example, the result of push 2 can be described by the following. So whatever the stack pointer is pointing to, at an offset of 0, it has a content of 2. So in this case, if I push 13 right after pushing 2, then the notation looks like this. Offset from where the stack pointer points to, because the stack pointer moves down in order to point to the new thing, which is 13 that I just pushed on the stack. So D plus 0 is actually 13, and then whatever we pushed earlier is now at D plus 1, or it is 1 byte off from where the stack pointer points to. So do we have any questions about this table? Because we are starting to shift our view from absolute addressing to relative addressing. In other words, relative to where the stack pointer points to, where do I find my stuff that I push on the stack? So are we good with this notation? Yes? Okay, all right. So now we move on to the rest of the mutual agreement between the caller and the callee, with a focus on just parameters and the return values. The mutual agreement between the caller and the callee starts with how the stack operates, which we described, and then we can now continue on to what happens on the caller side for a few things. If there are arguments, arguments are pushed in reversed order, which means the last argument is pushed first. Okay, so do we understand this particular statement? So if there are three arguments, let's say 1, 2, and 3 are the values of those arguments, then 3 is pushed first, then we push 2, then we push 1. Which one has the lowest address of the three? 1, 2, or 3? No. It is 1. That is correct. Yep. So remember that, okay? That is actually kind of important. Okay, all right. So we'll continue to read this. On TTP, arguments are pushed contiguously. There are no gaps between the items that you push on the stack. Now, I make this really clear because on any modern architecture, there might be gaps between the arguments. Because if you try to push a char, like a character, which is a single byte on the stack, when your architecture supports, 64-bit when there's a 64-bit processor, then there will be a gap. There will be a gap of 7 bytes between the char and the next thing that you push. The reason behind that has to do with, we want everything to be 64-bit aligned on the stack for efficiency when you have a 64-bit architecture, because each memory fetch operation from memory is going to retrieve 64 bits, which is 8 bytes. So we don't want things to be in between the 8 bytes, because that will require 2 fetches in order to get 1 item. Yep. Well, but char technically only has 8 bits, so you do not pad it. You simply leave 7 bytes completely unused in the case of a 64-bit architecture. So you would basically, when you push a char on the stack, you'll be pushing 8 bytes on the stack. The one that is at the least significant byte, or the one that is at the lowest address, is the actual byte that you want to push on the stack. The other 7 bytes are just random. They are just whatever was there to begin with. We simply don't even modify those. But I need to make this statement because when you work on a more modern architecture, that assumption is not true. The arguments are not necessarily contiguous. So in the case of the TTP, this implies the last argument has the highest address in a call frame. So a call frame is a name that refers to everything that a function needs in order to access the parameters, to get the return address, the address to return to the caller, and all the local variables. So those items collectively are stored on the stack, and that construct is called a call frame. Is that okay? All right. So we'll get back to the concept of a call frame from time to time, but right now we are just kind of focusing on two of the return address is on the frame, but the return value is not on the frame. So after you push all the arguments, then the return address is pushed on the stack. Is that okay? So relatively speaking, is the return address having a higher or lower address compared to the arguments? It's lower because the stack pointer starts with a high address, and then as we push items, the stack pointer goes lower and lower. So that means the most recently pushed item has the lowest address on the stack compared to the other items that are still on the stack. All right. So the return address is not optional because every subroutine, every function needs to return to the caller. So this is not optional. Um, and then after pushing all of these things, the caller will jump using a JMPI instruction to the entry point of the callee. And typically in this class, the callee, the function that we are calling, whatever the name of the function is in the C code, I just use exactly the same name as the label that defines the entry point in assembly code. All right. So that pretty much talks about everything from the caller's perspective for calling a subroutine. Okay, so this does not include the extra things that you need to do after the callee, after the function returns. So we'll talk about that in just again in a few paragraphs. So from the perspective of the stack pointer, okay, by the time you get to the callee, by the time you get to the function being called, the stack pointer plus 0, which essentially is just wherever the stack pointer points to, is the return address to the instruction immediately after the JMPI instruction, which means this is the return address back to the caller. If you have arguments, then the stack pointer plus 1 is argument 1, the stack pointer plus n minus 1 is argument n minus 1, and so on. Obviously, this is making the assumption that we are only pushing arguments that are only 1 byte long or 1 byte wide each. So is that okay? Do we understand this particular table and what it is trying to convey? Yes. hmm It does not matter, because 255 and -1 have exactly the same bit pattern. So once again, because when you're dereferencing a register, we are simply going to a location that corresponds to the bit pattern. Whether you want to call that -1 or 255 does not matter, because location 1111, 1111 is still the same location. So until you compare, remember, signedness only matters when we're comparing. So if you're not comparing addresses, then we don't really need to know whether we should look at the addresses as signed versus unsigned integers. But conventionally, addresses should be seen as unsigned integers. All right. So now we move on. Okay. So it also describes the callee should return to the instruction right after the JMPI instruction with the return address popped. So in the example, the stack should look like the following, okay, which is the same as this picture. Oh, right. So the callee should return to the instruction right after that because the return address is popped. So the key word here is the function, the callee, the function being called, is responsible to pop the return address. Okay, the increment D is associated with the callee, not the caller. So this is going to be important because if you forget that, then the stack is not balanced anymore. So by the time the stack, by the time by the time the function, the called function returns to the caller, this is going to be on the stack. You can see the only difference is the return address is now gone. The arguments are still on the stack, but the return address is now gone. Is that okay? So now the so at this point, the if there are arguments, the caller has the responsibility to clean up the stack by the arguments, which means in this case, the caller will need to add n to the stack pointer so that n bytes that were reserved by the arguments are no longer quote unquote on the stack. We do not delete content on the stack. We simply move the stack pointer to indicate whatever is below where the stack pointer points to are now available to be used again. Yes, because the caller is the one that pushed the arguments in the first place. Yeah, for the in a function call, the caller is responsible to push all the arguments before the JMPI to the function, right? So as a result, the caller code always knows exactly the number of bytes used in pushing all the arguments. The callee, on the other hand, does not always know. You mean the return address. So the return address is always pushed last, which means the stack pointer points to that, right? By the time you get to the call the function, the stack pointer points to the return address with all the arguments above it. But when the function returns, the function is responsible to pop the return address. So by the time we get back to the caller, what is left on the stack will only be the arguments. And then the caller will need to clean up the stack because those arguments do not need to exist on the stack anymore. All right, so that's kind of the perspective from the caller perspective. On the callee side, we already mentioned this. At the entry point of the callee, the stack pointer, which is register D, always points to the return address. This is the assumption. If there are parameters, the first parameter is going to be at the address or the location immediately higher than that of the return address, and so on. Okay, and this has to do with we push the arguments in a reversed order. So the first argument is immediately above the return address, and then the second argument is above the first argument, and so on. Are we still doing okay so far with this? I know this sounds really abstract. I will have a sample program to illustrate all of these points. And today's lab will also give you quite a few, examples to illustrate all of these points too. In the callee side, additional stack space may be utilized for local variables, but if that is the case, then the callee is responsible to move the stack pointer to move the stack pointer lower in order to reserve the space for the local variables. So we are not going to be focusing on local variables today, so we assume that there are no local variables at this point. All right. So this is kind of a picture of what the stack frame would look like when we have arguments, the return address, and local variables all on the stack. And this whole thing collectively is called the stack frame, the call frame. In other words, the call frame, basically includes everything that a function, the callee, requires. Okay, it has all the space for the local variables, it has the return address, and then it also has all the arguments for that particular function. So do we have any questions about this picture? We only have to focus on the return address and up because the variables, we'll talk about it in the next lecture. So we are good so far. All right. Okay. Moving on. Note that the local variables are not restricted to 1 byte wide. Arrays, structures, and so on, can also be variables. Can also be local variables. But we'll talk about that in the future lecture. To continue with additional agreements between the caller and the callee, there is no need to preserve the values of registers A, B, or C. The caller does not need to, the callee, I should take it back, because we're still looking at things from the callee side. So the callee, the function being called, does not need to say, oh, I'm messing up register B, and the caller may be using register B for something, and I need to preserve it. Nope. It is part of the agreement that the caller says, okay, you can mess up all the registers. Okay, I'm not making any assumption that any of the registers are preserved. So is that understood? Okay. At the exit point of the callee, if the callee has a scalar return value, then we use register A to store the return value. That's how we pass a return value from the callee back to the caller. It's using register A. So now the next question is, I'm sure there's a question in your head. Yes, there's there's no mechanism to lock a register because anytime you use LDI, a something, anytime you use, say again. But what do you mean by link? What do you mean by link? JMP without the I. Yes, but you only do that at the very end of the function. So hopefully, you're done using register A by the time we get there. The only thing is you have to remember register A is also used for returning the value of a function. So if you have a return value, then you don't want to use register A to pop the return address. You have to use register B or register C. That's the only possible contention. No, there's no place to put a lock. Assembly language programming gives you all the freedom. Every instruction will do exactly as it describes, assuming that you know what you're doing. So they put all the blames back on the programmer. The assembler does the minimum in order to translate the mnemonic into the opcode. That's all it does. Register A is used to return a scalar value. So if your function has a return value, then you don't want to use register A to pop the return address because the popping the return address happens after you specify the return value. So once you specify the return value in register A, then you only have register B or C that you can utilize to pop the return address. So we'll take a look at that code. Okay, so this is something that we're going to take a look at today. The call frame is so instead of going through this example, I have some additional examples today. So I think for the caller callee agreement, we can basically pause here, and then we can now move on to some sample programs that I can show you. So let's go ahead and show you some sample programs. And I am going to come up with new sample programs as we speak. In other words, none of this is prepared ahead of time. All right, so let me go to my trusty refer spider folder just so that like it's easier to run the programs. So I will usually from this point on, typically what I do is I will work on the C code and also work on the assembly code side by side. So it is easier for you guys to see the correspondence between the the C code versus the assembly code. So let me, I've never done this one before, so we'll go ahead and do it this way. So move the clock out of the way, and this is cmp.ttp.asm. Okay, side by side. So typically I want to do a stdint standard integer.h so that I can use uint underscore t, uint 8 underscore t, which is a 8-bit unsigned integer. Or if you want a signed integer, then you can use just int 8 underscore t. So these are all defined in standard integer.h, which you can also look up and find out what else it can define. So we're going to do a compare instruction here, and we'll do a signed compare. This is parameter x, this is parameter y, and all we want to do is to return whether x is less than y or not. Okay, in fact, maybe less than is probably a better name for that function. Okay, so obviously this is not a very useful function, but nonetheless, it is our example. Yes, it will return an int 8. Yeah, that's fine. So the compare is unsigned, but the return value itself is signed. Whether it's signed or not makes no difference because this is supposed to be like a Boolean, which means it's only a matter of 0 versus non-zero. -1 is non-zero, 1 is non-zero, 13 is non-zero, -65 is also non-zero. So I'm talking about plain C here. This is not C++. So we're still doing okay so far with this code. All right. So now we look at main. Okay, there we go. And we can do it like sort of like this. Okay. So we can now say if less than, and since we have not talked about local variables, I cannot use local variables. So I can now put in like a 6 versus a 255. Okay. If this is true, we do this. Otherwise, we do this. This is a return 0. And this is, I cannot really do a no op here, but I'm just gonna, put a no op in the assembly code to differentiate between the two branches. So that's the C code. The assembly code, which is on this side, starts with the entry code for the entire program. So unlike C code, where there's an entry code that you cannot see that implicitly calls main, and that's why from your perspective, main is the entry point of the entire program. In the assembly code, there's no such thing as a hidden entry code because we are actually going to specify the entire content of RAM. So we have to actually write the entry code, which is starting with the first no op instruction here. And then typically we want to pretend to initialize the stack pointer. I said pretend because every time you reset the processor, all registers will be reset to 0 anyway. Okay, but it's good to kind of remind ourselves that we have to reset the stack pointer to be one location after the last location in RAM, which is technically location 256. But because we have an 8-bit processor with an 8-bit address bus, so 256 is the same as a 0. So that's why I typically just write load D with a 0. And then we have to push the return address of calling main on the stack. So that is LDIA with the return address, decrement D, STDA. So that's for pushing the return address on the stack. And then at this point, we can do a JMPI to main. When main returns, then the whole program can halt. So this part is something that we talked about on last Tuesday. Okay, so the dot six plus notation was already discussed last Tuesday. So if you have any questions about that notation, I recommend you to review the lecture and or notes from last Tuesday. If you cannot understand that, then I can answer your question. All right. So now we have the function called less than. Okay, so from the perspective of less than, it is always nice to, well, guess what? I'm just going to put a halt instruction here, okay? Because I want you to be able to see what is on the stack, what is the stack pointer pointing to when we're at the entry point of the function. So we'll go to main, okay? So main is going to have to, so we have to call less than with these two as arguments. Can someone remind me which one I should push first on the stack? 255 or 6? 255. Thank you. Very good. So we push arguments in a reversed order. Okay. So, and for people who do not know which way we are supposed to push the arguments, you might want to ask yourself, why is it not registering? Okay. Because we mentioned this at the earlier part of today's lecture. So I was assuming that people would be writing down some notes, okay? Because the process of writing this down in your notes is actually important for you to kind of remember these things. Now, there is a reason behind why we push arguments in a reverse order, but I can talk about that later. But right now, we just say that this is part of the agreement. All right, so we just LDIA with 255, decrement D, STDA, and then we do LDIA with 6 in this case, decrement D, STDA. That's for pushing the 6 on the stack. And now we are ready to push the. Oh, can I do this now? Yeah, I'm so eager to call the function. Can I do it now? What am I supposed to push on the stack before jumping to the entry point of the function? I'm missing the return address. Very good. Okay, so that's good. Okay, I'm just trying to check to see if you guys remember, the convention. Okay, so decrement D, STDA. Okay, now we good. So this is when the function returns, it's going to return to whatever instruction I will be writing here. Okay, so I have not written anything yet. At this point, on line 27, when the function returns, the return address is gone because the function being called is supposed to pop it. But that means the 6 and the 255 will still be on the stack at this point. There's no need for those arguments to be using any space on the stack at this point because the function itself has already returned. So this is why we also need to increment D twice in this case, because the arguments, there are 2 bytes of arguments on the stack. They really should not be there anymore. Is that okay? So at this point also, because the function is supposed to return a return value of either a 0 or non-zero, depending on whether x is less than y or not. So now I need to use that to inform the conditional branch here, whether I should go to the first no op corresponding to the then branch, or the second no op, which is corresponding to the else branch. So that means I need to examine which register contains the return value. Register A, very good. Okay, so now we can do that little trick and AA, and then JCI, if it is non-zero, we go to the else branch. So now I'm going to use some really kind of explicit labeling, because I'm basically saying this is the else of the first conditional statement at the top level of main. Okay. Now, is it really necessary for this kind of program? No, it is not. Okay. But it is just a way for me to convey, you know, what that label is representing. Okay, which I think is important. Okay, because if I just use some random label like L1, L2, L3, L4, then by the time I define the label and specify code at the label, I might have forgotten what it means to be at this label. But because this is a if then else branch, we also know there needs to be a JMPI around the whole thing to end if zero to the end of the first conditional statement at the top level of main. So that label is going to be defined here. And you can see the way that I define the labels and the branches is non-linear. I'm working on the construct or the structure of the code first before I um, go back and stuff the branches with whatever they need to have. So here we have the first no-op instruction, and then here we have the second no-op instruction. So the no-op instruction on line 33 of the assembly code is corresponding to the no-op in comments on line 10 of the C code. The no-op on line 37 of the assembly code is corresponding to the no-op in comments on line 14 of the C code. So it is really important to make that association because you have seen this kind of code already. Okay, we have talked about compiling code from C to assembly code. I just skipped a whole bunch of steps because I just did everything in my head. Have been doing that since ninth grade. And I'm talking about my ninth grade, not yours. So many years. Because back in those days, programmable calculators were programmable using instructions that are not unsimilar to assembly code. How do you guys program your TI-80 something calculators? Huh? So it's a variation of basic. I see. So does that basic support structured um, control statements? Can you nest a conditional statement inside a loop? You guys are so lucky. You guys are so lucky. All right. So we are at the end of the conditional statement. This is corresponding to the end of the conditional statement, which is line 15 of the C code. So now we are ready. Main is ready to return to the entry code. Technically speaking, we need to do this because there's a return zero here. So the exit code of main is supposed to be zero. So we're gonna do it just because the C code specifies that. But at this point, now we basically want to do LDBD. This is retrieving the return address from the stack. This is for popping the return address from the stack. So one is for retrieving, and then the other one is for quote unquote deallocating the location that was used to store the return address. And then at this point, I can now execute JMPB to continue execution at the entry point code, which is the halt instruction, and that would conclude the execution of the program. All right, so I intentionally did not write any comments in this program, in this code, so that you can comment the program any way you want. So you can remind me to upload this program at the end of the class. I don't mind doing that, but I do not want to comment the code for you because I think going through the code and try to figure out what is this instruction doing within the context of the class is actually a good way to review the content for this class. So that's kind of part of the exercise that I want to kind of give you guys to do, which in a certain way, I'm saying this in a very mean way. Yes, I mean it to be mean. Um, so that means for anyone who's going to ask me questions about this, I'll be asking that person and go like, so what is the commented version of the code that I talked about on April 8th? Because I need people to be doing this. That part is on you, on the learner. Okay, if you have been doing this and you're still not quite getting, how things happen in this code, then I'll be more than happy to explain further, how, the whole thing works. All right. Okay. So this is your chance to complain. Was that mean or was that just tack? Would you describe what I said just as mean, or do you think it is just tack? Hmm? Can it be both? Yeah, tech can be mean. Or I should say, tech can be perceived as mean by people who want to interpret things that way. I'm the master of passive aggressive. Are you kidding me? Not that I actually pay attention to people's name when I'm grading. Yep, go ahead. Ah, you are correct. Well, we'll leave it like this and see what happens. Okay, but you are correct. Okay, good catch. So there's supposed to be a zero there. So I'm gonna leave that error in the program. So not knowing that I made a mistake on line 38, now I'm ready to kind of run this code to find out what it is going to do. And it's not going to do a whole lot, okay? Because what it will do is it will get to less than, and then it will stop at this halt instruction. But that was actually intentional because I want to show you guys what's happening to the stack pointer, what is stored on the stack, in what order, and how do you find all that stuff using the analysis tab of the assembler. Okay, so that's kind of intentional. The bug was not intentional, but I want to show you what happens when your program does not assemble. How do you know that your program did not assemble? Yep. Let me go back to the code so that you can refer to the line number. So line 3 is loading. This is how we calculate the return address, because the dot refers to the opcode of this particular LDI instruction. So the LDI instruction itself takes 2 bytes. So you can kind of imagine this is byte 0, this is byte 1, byte 2, byte 3, byte 4, byte 5, this is byte 6 from the address of the LDI instruction itself. So this is a relative way to compute the return address without using labels. But this is also what we talked about last Tuesday. I'm loading the address of the halt instruction. What? What? Okay, wait. What do you mean? What do you mean by 6 plus 1? Huh? Line 21. It is the same format. So it is the same calculation. Byte 0, byte 1, 2, 3, 4, 5, 6. I'm loading the address of the first increment D to register A over here, because that's where I need the function to continue execution when the function is done. All right. So when I assemble this correctly, you will actually get to see how this is all working. Okay. So we'll go ahead and start the assembling process. Um, did I? Oh, I forgot to save it. Yep. Go ahead. Say again. It might be helpful. Let me think. It is not required, but having it does not hurt because there are usually multiple ways to get to the answer. I just want to describe labs in general from this point on. So there are typically several ways to answer the questions in the lab. Even the what lab from last Thursday, there are usually multiple ways to answer the question. um, what I intend, okay, is for people to look at the code and then do the analysis in their head in order to kind of find the answer by analysis. Failing that, okay, some of the questions can be answered by running the code inside Logisim without River Spider, and then you can examine the RAM locations. Then you can count how many of those locations have changed. Okay, so that's that also works. Okay, and then using River Spider, you can also just look at, I think it's column C, and find out how many unique locations got changed so you can count those two. So there are typically several ways to answer the question, and more likely than not, um, answering the question by analysis is usually one of the options. So that's the long version of the answer to your question. Alrighty. Okay. So I just made a very typical mistake, which is I forgot to save the programs before trying to run them. Okay, so there we go. So this program has a bug, okay, well, I wouldn't say syntax, but it has a bug because I defined the label incorrectly, so it should not assemble. And this is what happens. After validating object code, the source code did not assemble correctly. Better fix the opcode first, or the source code first. So this is what you get when there's a mistake. So now the next question is, if there's a problem, what do you do next? Well, actually, the assembler will report errors. I would say it's not the best error reporting mechanism, but it will give you something. So you have to focus on column B. So right now we can see column B says, unresolved reference to main underscore and if zero, and that's exactly where the bug is. So now we go back to the editor here, and then we locate main underscore and if. The problem is not with the reference. The problem is with the definition not matching the reference. So there we fixed the problem. So you were correct. So good job catching that, before I ran River Spider. But running River Spider also gave me a chance of illustrating, how to how the workflow works in this case. How do you use River Spider? How do you know the program did not even assemble? And then where do you find the errors in the assembler? Okay, so now I can go back. Okay, so me being me, I need to go here, save the file again, go back to River Spider, and then just repeat the command. So hopefully this time it will tell me that everything is good. The program was assembled correctly and it ran. So yes, it did tell me that because it says your object code is good, starting simulator, the simulation's done, and by the time you read the message of trace data uploaded, check the analysis sheet, that means the analysis sheet should also be done. Okay, it should reflect the actual full trace of running this code. So now we go back to the assembler, and this time we go to the assemble tab first. Okay, the assemble tab is actually very useful, and that's why many assemblers, like commercial assemblers, would also give you a listing similar, not exactly the same, but similar to what you're seeing here. So we're going to focus on the LDI instruction with a .6 plus. So now we're asking, is 9, which is the second byte, which is the immediate value, is that the address that we need main to return to? Well, 9 being the address of the halt instruction is the correct return address. Then the second question is 9 actually 6 plus the address of the LDI instruction itself? The LDI instruction itself is the 6C, that's its opcode. It is at location 03. Now, I know column W is in base 16, but in base 16, 9 minus 3 is still a 6. So I hope that explains how the .6 plus works. Okay, the I think the only remaining question is why do we put the plus as the last thing instead of putting it between the dot and the 6? That has to do with the assembler is using RPN, reverse Polish notation, rather than infix notation. So you specify the operands, the numbers that you want to do something with first, and then you specify what the operation is. So that's kind of the general idea of RPN. Yep. Yes. So the dot is always referring to the current location of the current line, which in this case is location 03. Yep. Um, okay. In a very typical way, it depends. If you're trying to specify the return address in this kind of code, then you don't have a choice but to use 6 because only 6 is corresponding to the correct offset to where you need it to return to. That is correct. Yep. So you have to, whatever the number has to be has to match the actual offset to the location where you want the function to return to. Sorry? Yeah, right. It cannot go over 255. I mean, whatever this value turns out to be, if it is more than 255, it just get modded back to between 0 and 255. So everything is congruent modulo 256, basically. Yep. Yep. Go ahead. No, you cannot, because we're not trying to specify the instruction itself. We're trying to specify the location of the instruction. So before we use a label, so we use a label definition right before the halt instruction. So then we reference the label when we perform the LDI instruction. But that means you'll be susceptible to using the wrong label. Okay, especially for people who copy and paste code because, oh, calling is the same, I'm just going to copy and paste the code. So you can use the wrong label. If you use the wrong label, the program is syntactically correct because it's a label that does exist, but when the function returns, it'll be returning to a point that you did not expect. So those are bugs that are more difficult to debug. You can find it, it's just harder. I personally prefer doing it this way so that I don't have to worry about, oh, I need to come up with a new name for the label and I need to make a reference to the correct label. This is just, you still need to define the label halt one and so on. Yeah, yep. You can do that. Yep, yep. You can certainly do that, but I prefer not to do it. That's a kind of programming style kind of thing, and I do understand that everybody has a different style. All right, so this is the analysis, okay? The analysis is column C is particularly important in the analysis because every time we overwrite a location in RAM, in every push, column C reflects that. And column D is important for everything that has to do with D. It is important because register D is the stack pointer. This is how we initialize it. This is when we decrement it, and this is when we store to it. So on the column F and column G are also really kind of important, especially after you comment the program and then you run it, because everything in your source code will appear on column G. Column F is just the line number. So this means if you comment the code, you add the explanation of why this instruction is useful and what it is actually doing in the context of function call and parameter retrieval and whatnot. That means when you read the flow of the program, you are basically reading, oh, okay, at runtime, this is what's happening when the instructions execute. So I think that is also really important. Commenting the code in the source file is important because it is the analysis of how things are done. But when you run the code, the analysis tab will actually give you a sequential, a linear storyline of exactly what happens to memory locations, to registers, to the flags as the program execute. And I think that is equally important. Okay, so if I'm studying for this class, those would be the things that I would be focusing on. All right. So we can see it is pushing 9 on the stack. This is the return address from main back to the entry code. So that's the first thing we push on the stack. And then we push the 255 on the stack, which is argument 2 to the call of less than. And then we push the 6 on the stack, which is the first argument. And then we push the 19 on the stack. So the 19 should be the return address from less than back to main. So, but from here, we cannot tell, right? We go like, we have no idea whether that really is the case or not. So now you can go back to the assemble tab, go to location 19, and find out whether that really is the place where the where less than is supposed to return to. Yep, it is. Now, how do I know it is the correct location to return to? Because this is an unconditional branch. This code on at location 19 would be inaccessible if it's not for a direct jump, because it is right after a JMPI instruction. So that means, by the time we get to the JMPI instruction, the program will continue execution at the label of less than. This code is not reachable unless I have a branch of some kind back to this location. And in this case, it is the return from less than that would directly go back to location 19. Is that okay so far? All right. So I'll give you guys a little bit of time to formulate questions. Yes, please. Because, okay, I will see if the rest of the class remember. It is part of the caller callee agreement. That is correct. It is because the two arguments that we have collectively takes up 2 bytes on the stack. But now you have to remember which byte is each increment D deallocating. So I'm going to point to the first increment D. What do you think it is deallocating? Is it deallocated the first argument or the second argument? Yes, it is deallocating the first argument because the first argument was pushed last. Whatever was pushed last is either popped or deallocated first. Yes, it would jump to number 9 because that's what we push on the stack. Yep, that is correct. All right, so execution has not reached this point because I'm not done with less than yet. So now we can go back and try to complete the program called less than. But if you have any questions, about the code up to this point, now would be a good time to ask. Yes, location 19. Yes, until the next time you have a call or a return. Yep, go ahead. No, we store A to where D points to, and therefore the parentheses. Correct. You always allocate before you use it, and then you always retrieve before you deallocate. Correct. Yep. Unless somebody jumped directly to that location. Yep. And that would be main eventually jumping back to this location because of the JMP-B instruction right here on line 42. All right, very good. So that was a good discussion, okay? Because this is how I know whether you guys are understanding the concept or not. So now we can go back and implement the function called less than. So now let's go back to less than. When you implement a function, it is always good to have a mental picture at least of what is on the stack and where they are on the stack. So I'm going to use this notation. D plus 2 is going to be argument y, or the second argument. D plus 1 is going to be argument x, which is the first argument. And then D plus 0 is going to be what? The return address. Very good. Okay. So I'm glad you guys are answering these questions because I just want to see if you guys are understanding the material up to this point. So this is basically the entire call frame for less than because we don't have any local variables. So now the question is, so how do we retrieve the value of parameter x so that we can compare that to the value of parameter y? Okay, there are many ways to do it. Okay, so I'm going to illustrate two ways to do this. One way to do this is to copy register D to register C. So now register C also points to the return address, which is not what we want, right? So you can always increment C at this point. And then what is C at this point? When line 14 is completed, what is in register C? I'll give you, sorry, go ahead. Okay, is it the value of X or the address of X? Is the value of X. I mean, the address of X. Okay, yes. It is the address of X. Okay, after the increment C, it is the address of X. Are we comparing the address of X versus the address of Y, or are we comparing the value of X versus the value of Y? The value. Okay, so if I have the address in register C, how do I get to the value of where register C is pointing to? Yes. Which instruction do I use? You can use C. You can do it like this. So basically what this is doing, so in the assembly code, parentheses actually has a meaning. It means dereferencing. Okay, so I specifically made the assembly language to differentiate, are we accessing the register or are we accessing what the register is pointing to? So in this case, parentheses is the one that is dereferenced. And the copying is always from right to left, just like assignment statements in C and C++. So you can kind of try to remember those conventions because then it makes it easier to remember, oh, why do we have parentheses over here? And if, when there are two operands, which one is the one getting updated? It's always the first one. Okay, if anyone is updating, it's always the first one. Okay, so now register C has the value of parameter X. The other way to do this is to load the offset to a particular register. So in this case, I'll put it into register B. So the offset to register, not register, but argument Y is 2. So now I can say add BD. So at this point, after the add BD, register B will be the address of parameter Y. And then I can do exactly the same thing, which is a LDBB. So now register B has the value of Y, register C has the value of X. So now I can actually perform the compare, okay, to see if X is less than Y. So I do a CMP CB, which is computing C minus B, but without storing the result. In this case, a subtract would also work because I don't really care what is in register C after this operation. So, but I need a conditional branch here, okay, because it's a compare and it has to do with less than. So JXI to some label. The label is going to call, I'll call that less than return. Let's see, it should return a 1 in this case, which means the alternative is to return a 0, and then JMPI to less than exit, and this is less than. So I'll complete this part of the code, and then you guys can tell me what X is supposed to be. There we go. And there are many ways to do this, but right now I'm just doing it this way. And then we have the exit label defined here, less than underscore exit, which is the return code. Okay, so getting back here, what should I use instead of X? So is it L or is it C? Are we comparing signed or unsigned? We're comparing unsigned. So should we use the L flag or should we use the C flag? The C flag is correct. Okay, for unsigned comparison, we use the C flag. So we do a C over here. All right. And that's about it. Okay, so instead of a halt here, I can now replace it with the usual return value. But you can see how register A cannot be used anymore because I have already specified a return value in register A. So I cannot use register A for returning. So I can use register C, I can use register B, I just cannot use register A. So LDBD retrieve the return address, increment D to quote unquote pop the return address from the stack because that's the responsibility of the callee or the function being called, and then do a JMPB directly to go to continue execution at the location that B is pointing to. So there's a reason why JMPB, the B is not in parentheses, because the instruction itself is not really retrieving whatever B is pointing to. All it is doing is to overwrite the program counter with register B. And that is why in JMPB, the B is not in parentheses. All right. So I think the program is done. Okay. So can someone tell me by the time I get back to main from here, whether register A should be a 0 or a non-zero? If you look at the C code, what should less than return? It should return a 1. Okay, very good. So that means by the time I get back to main, which is the first increment D instruction here, register A should have a value of non-zero. In this case, we know it's supposed to be a 1. Okay, so I think we are done with the code. Make sure I save the code before I run it in River Spider. And there's another way to do this without using River Spider. It is just a little bit more involved. I think we have time today, so I can illustrate that process for people who have not yet set up River Spider. So, but before we do that, we go back to the analysis tab here. So this time, when we go to the analysis, we no longer has a halt instruction here. So that means we continue execution in the function. So CPR CD is in the function. FC, as we mentioned earlier, should be the address of X, which has a value of no. It's the first argument. So what was the first argument? X. It's a 6. So now we ask, there are two ways to answer this question. Okay, this is one way to answer the question. When we load C to C, it becomes 6. Okay, so that's one way to answer the question. But the other way to answer the question is we go to location FC and check out, oh, FD, sorry. So FD, because we have to remember to increment first. So we have to go back to the memory write operation and see whether we store a 06 into that location. So for that to happen, we have to scroll back a little bit, and we can see that we store a value of 06 into location FD. So that's why there are two ways to confirm that. Um, all right. So and then we load B with 2, which is the offset from where the stack pointer points to parameter Y, and then we add the stack pointer to register B. So that means FE is supposed to be the address of parameter y, which has a value of 255. Once again, there are two ways to confirm this. This confirms it too, okay? Because when we do a LD, we are accessing indirect and it got a value of FF. That's one way. The other way is to go back and ask, okay, what do we store at the location FE? And it is FF itself, which is 255. So those are the two ways to confirm that. And then we do the compare. Okay, so after the compare, you can see that the flags register is reflected here. So we can see that the carry flag is a 1, but the L flag is a 0. The L flag is a 0 because what does 255 as a bit pattern represent when we are looking at the signed interpretation? -1, exactly. Is 0 less than -1? Nope. And that's why the L flag is a 0, but the C flag is a 1. So this is one of the cases where if you use the wrong flag for the conditional branch, it would be branching incorrectly. Is that okay? So I'm using this to also illustrate the importance of specifying the correct flag depending on whether you're comparing things that are signed or things that are unsigned. All right. So now we do the JCI to less than return one. And it is going to take that branch because the carry flag is a one. So we continue execution at that label. We store a one to register A becomes one, and then we proceed to exit the code, exit the or return from the callee. We retrieve the return address into register B. So register A has the return value, register B has the return address. Okay, so they are completely different concepts. Okay, so one thing C really does not help is using a single return statement. We're doing two things. We are specifying the return value and we are returning back to the caller at the same time. There are programming languages out there where you can specify a return value, but not to actually return from this function yet. Yes. Um, yes, I could have written this entire thing using main, or I can have this entire thing in the unnamed entry code. The whole point of this program is to illustrate how do we pass parameters, how do we call, how do we retrieve the parameters, and how do we return. So I'll be writing a lot of programs of this nature where, oh, do we really have to do it this way? No, we don't. I'm doing it this way to illustrate a point. Is that okay? I mean, think about this. We only have 256 locations. That's combining the stack space with the code space. Okay. Do you think there are worthwhile algorithms that I can demonstrate in this class with 256 locations? I cannot do merge sort, but I can do the Tower of Hanoi recursively with 256 locations. But for the most part, no. Okay, for the most part, I cannot specify complicated algorithms. Okay, so that means whatever I demonstrate in this class has to do with um, illustrating how things are done, given the C code on one side, and then how do we translate that C code into assembly code. Yes, yes. Yeah, well, that's because the number of disk determines the depth of recursion. Um, I think I can handle like up to 8 disks or so. It's not too bad. All right. So to complete this, okay, so we are now back to let's see. Oh, right. So this is retrieving the return address. This is for deallocating the location that has the return address. So together, that is called returning from the function. And then we JMPB to continue execution at the location that register B is pointing to. So that's why we are continuing execution at location 2B. At location 2B, we have one increment D instruction for register D to go from FD to FE. And then we have another increment instruction to increment the stack pointer from FE back to FF. So now the stack is balanced. In other words, from the perspective of main, the stack pointer is once again pointing to the return address. Okay, so this is important because that is the agreement between the caller and the callee. The stack pointer should point to the return address before you return. So that's why the two increment instructions here seems like, oh, Tech, you're just being frugal with memory locations. No, it actually is super important because of the agreement between the caller and the callee. So by the time we get to okay, so then we have the instructions here. This is and AA. Okay, A is uh, it it is non-zero, so the Z flag is cleared. So if the Z flag is cleared, then we go to the else branch, and then the else branch is this node up here, which is, oh, I think I did it wrong, didn't I? I think I got the polarity of the conditional branch. Wait. I think I got it. Okay, line 51 is no, line 51 is the correct branch. Okay, I take it back. So if I go back to the editor, line 51 is corresponding to the then branch. Okay, so this is all good. Oof, okay, I thought I made a mistake and inverted the logic of the program. So this is all good. And then after the then branch, we have an unconditional branch to end if. Why is that necessary? In other words, why do I need line 52? Not line 52, is it? Yep, it is. So why do I need line 52? What happens without line 52? Yep, it will fall through the then branch into the else branch. In other words, it will first do the then branch and then it will also do the else branch. That is not the behavior of a conditional statement. So that's why the unconditional branch on line 51 is actually important. It is not just to make it go faster, it is actually important. So after that, we specify LDI A0. This is the return or the exit code of main itself, and then we retrieve the return address from main back to the halt instruction. We increment D in order to deallocate that location. And people may be asking, well, tech, surely we don't have to do that anymore because when we get to the halt instruction, the stack pointer is useless. Well, as a matter of playing by the rules, okay, playing by the agreement between the caller and callee, this is actually important, even though it does not change um, the effective code execution in any way. It is still important. So then we perform the um, indirect branch to whatever B is pointing to, and then we get to the hold instruction. So that concludes the demonstration that includes all the elements that I was trying to talk about today, which is how do we return the value? How do we pass arguments to parameters when we call a function? How do we access the parameters when we are in the function? How do we return from a caller back to the callee? How do we specify a return value? How do we deallocate the arguments from the perspective of the caller when the call is done? So this particular program illustrates every single one of those points. Yes. Uh-huh. Yes. Yep. So the thing about this particular instruction here is you do not want to increment D itself. Yeah. But But more importantly, okay, there is something about the locations that are below where the stack pointer points to. For the purposes of this class at this point, we're just going to be assuming there are gremlins, okay? And all the locations below where the stack pointer points to, the gremlins are free to mess them up. So unless you're sure that you don't need to maintain the content of a location, do not increment register D, because the moment you increase the stack pointer, whatever it used to point to can now be modified or messed up by the gremlins. Okay, so I will further explain what the gremlins are in the future, but right now we just say, oh, you don't want to increment the stack pointer unless you are sure whatever it was pointing to is no longer useful to you in the future. All right, so you do need the access code of today's lab. So let me give you that first. Okay. So today's lab is called params and return value. And I'm letting you guys have infinite retries again. Why do you need that? It's psychologically it is just a little bit more comfortable. Yep. Okay. It is a WT frame. What the frame? I hope that's easier for you to remember. WTF? All right.